Well, in this lecture, I'm going to be explaining another important article for future learning, and we use contrastive representation. But contrastive learning, you can do it using you can implement it in a supervised setting or in a self-supervised setting. But here in this article, they focus on supervised contrastive learning. And they use the transformer and classification. So I'm going to be focusing on this paper in 2022. Future learning as an emerging problem has attracted intensive attention in computer vision, for example. Mostly in computer vision, because in NLP there are a few papers in comparison to computer vision. Recently, massive works concentrate on exploiting meta-learning to improve performance of recognition. However, most of them overlook the intra-class and inter-class relationship within the support set during episodic training, which are significant and important for a task of downstream. To tackle this problem, we present an efficient supervised contrastive representation embedding for few-shot classification. So we employ swing transformer, a kind of transformer, swing transformer, as the backbone to replace the convolutional neural network architecture in order to explore the huge potential of transformer-based backbone for the field of future learning. We introduce supervised contrastive laws to meta-learning to take good advantage of extremely limited relations for the first time. This is the framework of supervised contrastive representation embedding. So in future learning, we always have support set in each episode and query. And in contrastive learning, we always have positive samples and negative samples. So we divide the support set into positive and negative samples because we can, and they do augmentations for negative side in a different swing transformer. They do augmentation again using swing transformer, but they repel each other. So we have a loss that represents this supervised contrastive loss. The reason is that because we have given the data, we are not using any kind of self-supervised data augmentation. And here we have also metric-based learning, and so this is the difference in batch exploitation between prior work and this present work. As you see, we care about the relation. For example, these are positive pairs and negative pairs. We care about if they repel or attract each other. In contrast to previous works that they just ignore the relationship. They just ignore contrastive learning. So again, we have KV N-shot problem. So we have N examples and K classes. We have support and queries as a standard. But we employ supervised contrastive laws to evaluate the similarity between the feature vectors from positive examples and negative examples. The other way is that H sub I are put into the classifier, where we collect the feature vectors of all examples with the same labels to average them so that we can get a class representation. Those are prototypes that we always call. And here, for each batch, we randomly choose an image as an anchor point, an anchor image in the support set, and we combine the anchor and the other images that have the same label as positives. The same thing for negative. The remainder images of support set with different labels constitute the negatives. And we use this kind of transformer architecture, which is called swing transformer, for our backbone. And then we use projection that consists of multi-layer perceptron to convert anchor and the remaining samples into feature vector space, Z sub i's and Z sub b, and then the rest of that is just contrastive loss that we are familiar with. So we take the average of the feature vectors belonging to the same class to represent features. So the same thing, it's very easy to take average. Of course, I've seen some papers that instead of simply just averaging, they use attention. They discriminate between different examples, different shots. And here F is the backbone that we use for swing transformer. The rest of that is just the softmax. We give the softmax to the negative distance between samples and classes. And this is the contrastive entropy, cross entropy loss, and this is the contrastive learning that we are using, and we use this lambda as a hyperparameter. Then you can see that they have done it for CFAR 100, and the accuracy for one shot, which we expect to be lower than 5 shots, is 47, which is less than 60. We expect that because we have only 1 shot in contrast to 5 shot, and both of them are for 5 classes, so it is fair. And if you compare it with mammal, I think I have explained in maybe 3rd or 2nd lecture of the current playlist. I've explained this protonet in as well. If you compare it with protonet, it 5%, 6% more, then you get 47. Even for this 5 shot, you see improvement. And they also do it for mini ImageNet. They compare it with mammal and RelationNet. I think I have explained this as well. RelationNet. And it's better than mammal. So this paper works better than mammal. 20%. If you add 20%, so this method is better. The accuracy is better.